It is 1991. A research vessel called the Nautilus drops anchor somewhere in the middle of the Strait of Gibraltar. The mission seems simple enough. Drill 5 meters into the seabed, pull up some rock samples, and go home. Routine, straightforward. Almost boring. The drill begins its descent into the dark water below. And then, without any warning at all, something goes terribly wrong. The entire ship begins to shake. Not gently, not slowly, violently, like a plastic toy being thrown inside a washing machine. The steel drilling cable stretches to its absolute limit, threatening to tear straight through the deck. The captain looks at his crew, looks at his instruments, and makes the only decision available to him. He orders an emergency abort. The cables are cut. The mission is over before it even properly began. No storm caused this. No mechanical failure, no human error. The ship simply could not hold its position in this water, not even for a few minutes. And that is the moment when the questions started to get very serious. What is really down there?
Humanity has sent rovers to the surface of Mars. We have built tunnels beneath the Swiss Alps. We have placed bridges across open ocean.
And yet, right here in this narrow strip of water separating Europe from Africa, measuring just 14 kilometers across, something has stopped us. Something that has defeated the greatest engineering minds on Earth for over 100 years. Something that has swallowed entire blueprints, entire government budgets, and entire careers. This is the story of the most impossible 14 kilometers on the planet. And what you are about to learn will change the way you see this world entirely. Stand at a viewpoint called Mirador del Estrecho on the southern coastline of Spain. Look south. On a clear day you will see it. Not on a map, not through a telescope, with your own eyes. A mountain rising from the sea on the African side. That is Jebel Musa, in Morocco. 2 entire continents separated by what looks like a wide river. 14 kilometers, that is all. To put that in real terms, it is roughly the same as driving across a mid-sized American city. On a high-speed train, you could cover it in under 3 minutes. A fast boat would get you across in less than 30. And yet, despite everything humanity has achieved, not a single bridge or tunnel connects these 2 landmasses. Not today, not ever. Now think about what passes through this narrow gap every single year. Approximately 100,000 ships make this crossing annually. That works out to more than 270 vessels per day, moving through a corridor just 14 kilometers wide. Inside those ships you will find 33% of the world's entire oil and natural gas supply, 50% of global trade. And 80% of all merchandise exchanged by the European Union passes through this one thin crack in the boundary between 2 continents. This is one of the most strategically important waterways on the entire planet. And it has no fixed link, no bridge, no tunnel, nothing. In 1979, the King of Spain, Juan Carlos I, and the King of Morocco, Hassan II, signed an agreement. They made a solemn promise. They would find a way to connect their 2 countries, to connect 2 continents. They established 2 state companies, Sechexa in Spain and SNED in Morocco, and gave them the mission of studying this crossing until a viable solution was found. That was 45 years ago. China constructed the Hong Kong to Zhuhai to Macau bridge, 55 kilometers long, in just 9 years. The Channel Tunnel, connecting England and France, stretches 50 kilometers underground and was completed in just 6 years of actual construction. Engineers have bored through the Swiss Alps, drilled beneath Tokyo Bay, and placed massive structures across active fault zones the world over. And here at 14 kilometers, they have failed. Completely, repeatedly, without exception. The question is not just why. The question is what exactly is hiding beneath this water that makes it unlike anywhere else on Earth.
The first person to look at this gap and think on a truly grand scale was a German architect named Hermann Surgel.
The year was 1920. Europe was still broken after the First World War. Economies were shattered, and people were hungry for bold ideas. Hermann had one. He called it Atlantropa.
His plan was not to build a bridge across the Strait of Gibraltar.
His plan was to make the water itself disappear. The concept was this: build a massive hydroelectric dam directly across the strait. block the inflow of Atlantic water into the Mediterranean Sea. Without constant replenishment, the Mediterranean would begin to shrink. The water level would drop by as much as 200 meters. Vast stretches of new land would emerge from the seafloor. Europe and Africa would physically join into one single connected landmass, a new continent. Hermann was not sketching ideas on napkins. He calculated everything. He knew that if the Mediterranean dropped, ships traveling from the Red Sea would face a massive height difference. His solution was a system of lock chambers, identical to those used in the Panama Canal. A vessel enters a sealed chamber, water drains, the ship descends to the new level, the doors open. The same technology that works in Panama applied here. He calculated that he would need not one dam, but several. At the Dardanelles between Turkey and Greece, between Sicily and Tunisia, an entire network of structures reshaping the Mediterranean basin. He spent 3 decades lecturing across Europe, publishing detailed books and lobbying governments without stopping. But the world said no. The cost would have exhausted the budgets of every European nation simultaneously. Scientists warned that draining the Mediterranean would turn its coastlines into dead salt deserts. Ancient cities would be stranded. Ecosystems would collapse entirely. Hermann Sörgel died in 1952, still believing, and Atlantropa was quietly filed away. Decades later, in the late 1990s, a different kind of visionary appeared. An American architect named Eugene Tsui designed something no one else had imagined: a floating bridge. Not a traditional structure with pillars sunk into the seabed. Tsui's design floated on the surface of the water, anchored by triple cables to both coastlines. It would begin on the Spanish coast, submerge beneath the surface for 2 miles to let ships pass overhead, and then rise again at the center of the strait, connecting to something extraordinary. A floating artificial island, 3 miles wide, rising from the middle of the sea. On this island, Tsui planned 24 lanes of roadway, multiple rail lines, wind turbines, solar farms, public parks, waterfalls, theaters, and a 23-story tower. Not just a crossing, a new destination, the 8th wonder of the world. The structure would be built from waterproof concrete reinforced with stainless steel and anodized aluminum, shaped like a fish with a central spine and loosely connected sections that could flex in strong currents rather than resist them. Triple cables on both ends would anchor it to the coastlines, allowing the entire structure to move with the water. The estimated cost was around $1 billion. The vision was unlike anything that had come before. But then the geological surveys came back. And what they revealed ended every plan that had ever been drawn. By the time serious engineering teams began examining the shortest crossing point,
the canyon route between Punta Camarinal and Punta Sires, the data was already telling a disturbing story.
the depth of the water at the narrowest point is not 50 meters. It is not even 100. The canyon beneath the Strait of Gibraltar reaches a depth of 900 meters, very nearly 1 full kilometer straight down into darkness. Think about what that means. Stack 3 Eiffel Towers on top of each other, end to end. That entire structure still would not reach the bottom, and every single bridge pier needed to support a crossing here would have to descend to at least that depth. Built underwater, in churning currents, in one of the most seismically active zones on the planet. What about a tunnel? The deepest undersea road tunnel ever built, the Ryfast Tunnel in Norway, descends to 292 meters below sea level. This route requires going to 900 meters, more than 3 times deeper. At that depth, water pressure can collapse a steel barrel flat in a fraction of a second. The forces involved are not just challenging, they are in a completely different category from anything engineers have dealt with before. The seabed itself compounds the problem in ways that surprised even experienced geologists. When research teams finally extracted core samples from beneath the strait, they found that the upper layer of the seabed consists primarily of a geological material called breccia, a mixture of broken rock fragments suspended in a soft clay matrix. Breccia is considered one of the weakest and most unstable foundation materials in existence. It is highly porous, prone to sudden collapse under load, and notoriously unpredictable under drilling. Anchoring bridge piers into breccia is like trying to drive fence posts into wet sand. The structure would shift, tilt, and collapse without warning.
Below the breccia lies the opposite problem entirely.
A layer of extremely dense igneous rock formed under immense pressure over millions of years. So hard that drilling equipment sent to test it came back damaged. Drill bits fractured, cables snapped under vibration. You cannot build foundations in the weak material above. You cannot drill through the hard material below. The strait traps you between two kinds of impossible. But even the depth, the breccia, and the impenetrable rock are, in theory, engineering problems. Enormous problems. But ones that, with enough resources and time, could at least be approached systematically. What lies at a deeper level cannot be solved with money or technology. Running directly beneath the Strait of Gibraltar, like an invisible fracture in the foundation of the world, is the Azores to Gibraltar Transform Fault. The active boundary between two of the largest tectonic plates on Earth, the African plate and the Eurasian plate. These two colossal slabs of crust are not resting. They are moving, constantly, grinding against each other, accumulating pressure for centuries before releasing it all at once. This fault is not historical. It is alive and active right now.
On the 1st of November, 1755, it released an earthquake of devastating force.
The city of Lisbon was destroyed in minutes. Buildings that had stood for 5 centuries collapsed into rubble. A tsunami swept across the Atlantic Ocean. Fires burned through the city for 5 days straight. Between 60,000 and 100,000 people were killed in a single morning. One of the worst natural disasters in European history, caused directly by the same fault that runs beneath this strait today. On February 24, 2004, it struck again. An earthquake near the Moroccan coastal city of Al Hoceima, magnitude 6.4. Over 600 people killed, thousands injured. In September 2023, Morocco was hit once more. Magnitude 6.8 near the High Atlas region, nearly 3,000 people killed. Ancient villages built from mud, brick and stone collapsed in seconds. Rescue teams spent days digging through rubble. The ground beneath this region is not stable. It has never been stable, and there is no geological evidence it is becoming more stable. Now imagine building a bridge across this fault. Half the piers anchored in the Eurasian plate, the other half in the African plate. These plates do not move together. They shift independently in different directions at different rates. Even a minor seismic event, a tremor too small to feel on the surface, could displace both sides of the bridge simultaneously. The deck buckles, the cables snap, the entire structure falls into the water in seconds. A rigid concrete tunnel offers no better outcome. Picture a glass tube placed across 2 conveyor belts moving in slightly different directions. When one belt shifts, even by a few centimeters, the tube breaks in 2. A pressurized concrete tunnel through an active fault zone carrying passengers at 200 kilometers per hour faces exactly that scenario, not gradually, instantly. And the currents of the strait itself make even conducting a survey nearly impossible. This strait sits at the collision point of 2 fundamentally different bodies of water. To the east, the Mediterranean, warm and highly saline from centuries of evaporation. To the west, the cold Atlantic, carrying polar-influenced water southward. Where these two meet inside the narrow confines of the strait, they do not blend. They collide. Warm, lighter water rises toward the surface. Cold, heavier water sinks toward the bottom. This creates powerful vertical circulation churning throughout the water column at all times. Surface currents regularly reach 11 kilometers per hour. Winds gust to over 108. Research vessels trying to hold position for drilling surveys were thrown sideways by forces they could not counteract. Anchors dragged. Drilling cables snapped under the lateral strain. Mission after mission was aborted before any meaningful data could be gathered. The conclusion was devastating and final. The shortest route was not just difficult, it was, with any technology currently available or foreseeable in the near future, impassable. In 2005, a research vessel called the Kingfisher was dispatched on a mission with a completely different approach. Instead of heading directly for the narrowest crossing, the captain steered west, away from the canyon, away from the fault, away from everything that had stopped every expedition before. Day after day, the crew swept the broader seabed with sonar, mapping topography that had never been fully examined. And after weeks of patient, methodical work, they found something extraordinary, something that had been there all along, completely overlooked. A submerged ridge, a natural underwater shelf rising from the seabed, stretching from Punta Paloma near Tarifa on the Spanish coast to Punta Malabata near Tangier in Morocco. Geologists call it the Camarinal Sill. The depth above this ridge is 300 meters, not 900, 300. A difference of 600 meters that changes the entire equation. 300 meters is still an extraordinary engineering challenge, deeper than any undersea tunnel ever successfully built. But it is a challenge that exists within the boundaries of what serious engineering can attempt. The seabed composition here is also more workable. Less of the catastrophically unstable breccia that dominated the canyon route. Thinner layers of hard igneous rock below it. The geological conditions are not simple, but they are dramatically, fundamentally more feasible than the direct crossing. The route is longer, 28 kilometers instead of 14. When officials publicly acknowledged this, stating that engineers were now planning to build twice as far to achieve the same connection, the reaction was swift and cynical. People accused governments of deliberate delay, of commissioning study after study as a performance of progress, while delivering nothing real. Online commentary filled with ridicule. Politicians who had promised to connect two continents had become objects of open mockery in both countries. But the engineering reasoning was not politics, it was practical necessity. 3 of the 5 critical problems on the canyon route are substantially reduced on the Camarinal Sill. The depth is reduced to a third. The seabed is softer and more workable for modern tunnel boring machines. The hard rock is less dominant. What remains is still the presence of the fault system, still running beneath the western strait, and still the cost, which geology cannot reduce. The plan that emerged from years of survey analysis is not a bridge. Bridges were permanently ruled out for every possible alignment across this strait, due to the combined impossibility of depth, currents, and seismic exposure. What engineers are now targeting is a tunnel system. 3 parallel tunnels bored through the Camarinal Sill formation. 2 tunnels carry high-speed rail traffic, 1 in each direction, with trains running at over 200 kilometers per hour. The third tunnel runs between them as a dedicated service corridor for maintenance crews, ventilation, and emergency evacuation. The crossing connects Spain's national high-speed rail network on the European side to Morocco's Alborak high-speed railway on the African side. Alborak, Africa's first high-speed rail line, has been running between Casablanca and Tangier since 2018 and already uses the same track gauge and electrical systems as the Spanish network. In December 2025, the German tunneling firm Herrenknecht released a formal engineering study commissioned by the Spanish government. Their finding was unambiguous. The tunnel is technically feasible using current tunneling technology. Modern tunnel boring machines of the type deployed on the Bosphorus crossing in Istanbul and Madrid's M30 motorway tunnels could be adapted to the depths and geological conditions of the Camarinal Sill route. If completed, the journey from Casablanca to Madrid drops from 12 hours to 5.5. The tunnel could serve up to 12.8 million passengers annually at capacity. For the first time in over a century, the engineering path is visible. But technically feasible is not the same as built, and the distance between those two words is where this project has lived for over 100 years. The full cost of the tunnel, including rail connections and terminal infrastructure on both sides, is currently estimated at 15 billion euros or more. That figure has grown with every updated analysis. No binding financial commitment has ever been signed by any party. The timeline tells the same story from a different angle. In 2006, engineers told journalists with apparent confidence that the tunnel would open by 2025. That date has passed. The current projected completion is 2040. A delay of 15 years for a tunnel that would take 10 to 12 years to physically build once boring actually begins. Between 2016 and 2021, the Spanish government allocated just 50,000 euros per year to Seismic, the company managing the project. It rose to 100,000 in 2022 and 750,000 in 2023. The European Union contributed 2.3 million euros for a design study. Herrenknecht Iberica received 296,000 euros in 2024 to assess drilling feasibility at the Camarinal Sill. Total expenditure on research and feasibility across the full life of this project now exceeds 50 million euros. 0 euros have been spent on construction. In 2024, something quietly strange occurred. A seismic monitoring study had been contracted to a company called Tecpam Ingenieria, specifically to measure earthquake activity along the proposed tunnel route. This was among the most critical data the project required before any construction decision could be made. Then the study was suspended. The official reason given was security concerns raised by the Royal Institute and Naval Observatory of Spain. No further explanation was provided to the public. The study has not resumed. What the monitoring found, or what it was approaching when it was stopped, has never been disclosed. There is another layer that almost never appears in formal engineering assessments, but sits quietly behind every conversation about this project. In 2024, the Strait of Gibraltar recorded the highest number of unauthorized crossings in its documented history. Thousands of people attempting the passage by inflatable boat every month, many fleeing poverty across North and Sub-Saharan Africa. The strait is already a site of immense human tragedy alongside its role as a global trade artery. Critics have argued with considerable force that a fixed rail link between Africa and Europe would fundamentally alter migration dynamics in ways that neither Spain nor Morocco has ever addressed in any public document. That argument has never appeared in an official technical assessment, but it has also never been formally dismissed. And beneath all of it is a question that no government report will ever address directly. The Strait of Gibraltar is one of the most strategically valuable maritime choke points on Earth. Whoever influences traffic through it holds significant geopolitical leverage over global commerce. A permanent fixed link would change that equation in ways difficult to fully predict. There are national, commercial, and strategic interests that benefit from the current arrangement remaining exactly as it is. Whether those interests have ever shaped the pace of this project is something the official record will never confirm. For more than 100 years, the finest engineering minds this world has produced have looked at this 14-kilometer gap and seen possibility. They came with blueprints refined over decades, with technology that had already conquered mountains and ocean floors elsewhere. Hermann Sörgel devoted his entire life to this crossing and died with nothing built. Eugene Tsui drew a floating city on the sea and watched the drawings disappear into filing cabinets. The engineers who built the Channel Tunnel arrived here with confidence and left quietly. Ships that could cross oceans were thrown around like bathtub toys. Drill bits that could bore through granite fractured 900 meters down. Mission after mission was aborted. Study after study produced more questions than conclusions. In December 2025, when Herrenknecht confirmed the tunnel is technically feasible, many people called it a turning point. Progress at last, the beginning of the end of this long wait. But technically feasible is not built. The Channel Tunnel was technically feasible long before the first boring machine ever turned beneath the English Channel. The gap between possible and real is exactly where this project has lived for over a century. It is not filled with water. It is filled with money that was never committed, timelines that keep sliding forward, deadlines that keep disappearing, and a seismic monitoring study that went quiet for reasons no one has explained. Engineers who worked on this project have said something privately that they do not put in official reports. They say the real obstacle has never been the geology, not the depth, not the breccia clay, not the fault line. Those things are real and formidable. But they are technical problems, and technical problems can eventually be solved with enough will and enough resources. The real obstacle is something harder to map and harder to measure: the absence of genuine collective commitment. The willingness to look at this gap and truly decide that it will be closed, with decisions that cannot be reversed by the next election cycle or the next diplomatic dispute. The Strait of Gibraltar does not negotiate. The currents that tore the cables off the Nautilus in 1991 are still moving today, at the same speed, in the same directions. The fault beneath the seabed is still accumulating stress, still grinding, still building toward a release that no instrument can predict. The 900-meter canyon on the short route is still there, unchanged, cold and dark and patient. And the gap between Spain and Morocco is still exactly what it has always been. 14 kilometers of water, the same distance it was when the first engineer looked at it and believed it was possible to cross. Somewhere inside those 14 kilometers, between the engineering reports and the suspended seismic studies and the promises made by kings who are long gone, something continues to hold two continents apart. Whether that something is the Earth itself, still refusing to be connected, or whether it is the people who have every reason to keep it this way. That is a question this project may never be allowed to fully answer. The gap is still there, and the world is still waiting.